Welcome. In this short video, I'm going to introduce you a simple neural networks computational model. The very basic foundation for computational steps are few things in neural network. One of them is how do we calculate given certain input values and the weights that are represented as arrows given some input values and the weights that are connecting these input neurons to an output neuron, is that you take a weighted sum of these input values by the weights given by these arrows, and that is called the input value to the output neuron. But then we use an activation function to modulate that, using some kind of a transformation. In this case, this is called a sigmoid transformation, and that is our activation function. There are many other activation functions available. I will give you a reference for that, and use an activation function, in this case a sigmoid function, and apply that activation function for the weighted sum of input values weighted by the arrows, indicated arrows. That will be called the cell value, output value for this output neuron. Okay, cell value, output value for the output neuron. So that is the basic foundation, and we are going to apply that kind of computation, product sum or sum product. Sometimes it's in Excel it's called sum product. Sum product sum or sum product are the weights with the input values, and use an activation function on that. That fundamental principle again and again will be used in this actual calculation model. So in this model we are talking about two input neurons and two hidden neurons in one hidden layer and one output neuron. And the model here is an following example. So let's say an individual wants to make a decision, and he is neutral right now, and he's trying to make a decision whether he should vote for GOP or Democrat. And GOP, and he gets input values from two different people. One is the spouse, the other one is the parent, let's say. So the spouse is giving input value of 0.35, which means 0 means, let's say, closer to 0 means GOP, closer to 1 means Democratic Party. So spouse gives 0.35, parent gives 0.9, and those input values are weighted by these corresponding arrow values, right? The arrows refers to, connectors refer to the weights to be attached to these input values. So it's 0.35 times 0.1 plus 0.9 times 0.8 goes into this first hidden neuron, and similarly 0.35 times 0.4 plus 0.9 times 0.6 goes into second hidden neuron. But then that needs to be modulated with the activation function. We use sigmoid function, and when you apply that activation function, whatever you get, that value is the output value from this neuron. Okay, and that is exactly what is going on here. 0.35 times 0.1 plus 0.9 times 0.8 equal to 0.755. Apply the activation function, you get 0.68. That is the output value from here. That becomes the input. That becomes the input for this output neuron. Okay, so that value is 0.68, and similarly this value is 0.6637. Okay, and now you are using those as input values weighted by this 0.3 and 0.9. Whatever you get is here 0.80, and again you apply the activation function, logistic activation function, you get a 0.69 value. Okay, now you got values here also similar to this one. Now nonetheless, whatever the value you get is 0.69, but you are neutral. Let's say that is represented by 0.5, and so the error is 0.69 0.69 minus 0.5. Okay, or 0.5 times or 0.5 minus 0.69. So the error is 0.19. Okay, or minus 0.1. Either way, it's okay. So the error is that error is 0.5 times 0.69, but we need to back propagate their error, so that if we need to modify these weights, it's okay, modify it, but the purpose is to reduce the error, what the network says as the value versus the individual who has a value of 0.5. That error goes down to 0, very close to 0. That is the goal of building the network and building the network means estimating these weights. That's as simple as that. Okay, so we have done that one forward pass, and we got the output value to be 0.69. The error is, we got the error to be minus 0.19. But nonetheless, we want to back propagate this error so that, in order to modify these weights, okay, and as you do that back propagation, these weights will get modified, but then you can use those new weights to again do the feed forward, and you will keep doing this, feed forward, back propagate, feed forward, back propagate, and so on until the changes in these weights are minimal. Okay, a sum set parameter, minimal parameter. Okay, maybe it is 0.001. Okay, and we say the network is converged, and we can use the network for future prediction, and that is what the second step is. But when we back propagate, we need to use in which direction we need to change the weights, and that is given by the first derivative of the activation function. In this case, first derivative of the activation function is the activation function is f. Let's say the first derivative is f times 1 minus f, and that's what this value is, o times 1 minus o. Okay, the output value, whatever we have, the output value, we are going to use the back propagation gradient, and that is o times 1 minus o. So the output error is 1 minus 0.69 times 0.69, and the differential between the individuals value versus the network value is t minus o, so that is minus 0.19, and that is weighted by this value. Okay, and that value turns out to be minus 0.0406. Now we back propagate this error to all the weights, so that the weights and the previous weight values are all modified. Okay, the purpose being modified in such a way that next iteration you will have less weight, right? And that is assured by the theory. If you use this this kind of gradient back propagation method using gradient values, you will reduce the errors, and that's what you're going to see here. So the output error is, we just saw that output error calculated value is minus 0.0406. Now we want to modify 0.3 and 0.9 and also 0.1, 0.8, 0.4, 0.6, and those are done by this method here. So 0.1, W1 plus, W2 plus are the new modified values. So you modify this 0.3 and 0.9 here, that you have here 0.3 and 0.9, and you modify that value using the error that we got. Okay, and that error is 0.0406 times 0.68, that this value 0.0406 times 0.6637. In the same way, now we calculate the errors for the hidden layer. Like the output layers, we calculate the error, we are going to do for the hidden layer neurons, and that is what this one, always this, the gradient is f times 1 minus f or o times 1 minus o. Okay, so the new values of the errors for the hidden layers is, you are going to, the original error is, the overall error is this much, and we are going to continue to modify that using this, whatever we calculated the weights times the o times 1 minus o, and the calculated value is this one. And we do the same thing, the calculated value for the W1, W2 we know now, and that is minus 2.406 times 10 power minus 3 minus 7.916 times 10 power minus 3, and that is used to modify now the W3456. Okay, that is this one, W3456. Okay, and that is what is done here. So these are the original weights, and we are modifying it by these adjustment values here, which uses the hidden layer errors, and we are we are multiplying that with the corresponding 0.35 and 0.39, 0.35 and 0.9, 0.35 and 0.9, which is coming from these input values. Okay, the first input values. So that's how we modify the the weights for the W3, W4, W5, W6. Now, once you are given, you can feed forward now using these values, and you will get a new error value minus 0.18205, and original error was minus 0.19, and now you have reduced error, and that's how it will happen. It will continuously it will reduce, and when you are satisfied with the sufficient reduction, you call it a solution, and that means the network converged. Now there are a few things that you have heard of it in this process. I will recall those things. I talked about weights, I talked about activation function, I talked about input neuron values, I talked about the output neuron values, error in the output neuron, final output neuron, and then how we back propagate that. We feed forward and back propagate and repeat this one again and again until the weights are until the error is reduced to a minimal, okay, in the output neuron. And at that time, whatever the weights you have is the final weights for the network, and that defines the estimated network. Now you can use that to predict. We also talked about we want to talk about one more item, that is in this case I used one observation to do the calculation, but if you have 100 observation, then you get 100 observation and you take the average value. For each of the observation you are going to calculate this thing, and then you take the average of the weights. That is your solution. Now what if I have 10,000 observation or 1 million observation? Then you have to batch process it, so you chunk them into 100 or 1,000 like that. For each of them you calculate this full collection of 100 for the 1,000 observations total, which is 10 hundreds. When you go through 10 cycles, then it becomes one epoch for a given starting point, 0.1, 0.8, 0.4, 0.6, 0.3, 0.9. And it doesn't have to be, remember those are all random starting values. So you can redo this for again another 100 observation. That is the next epoch. So you do 10 epochs, then it becomes a one solution, full solution. Average of those weights when you do the 10 epochs becomes a full solution. And the learning rate is another one. The concept that I wanted to introduce to you is what is called the learning rate, and that is that one I'm going to bring it up to you here. Okay, here it is. The learning rate is a hyperparameter that controls how much to change the model in response to the estimated error each time the model weights are updated. So you don't want to take, I didn't adjust that, make that adjustments here because it will become a lot more computed values, complicated work and so on, which computers can do much better job. So you want to take only a certain weights of the weight changes. No, you want to take a small weight changes, not too much weight changes, and that is what your learning rate is. Okay, so this defines the simple computational neural network and how the computations are done, and eventually when the loss value, in this case the difference, we took the difference, but it could be square of the difference in the output neuron, that whatever the minimal value you want to achieve, assures you the network is estimated properly. Okay, thank you.